Okay, so as I mentioned in the previous video, now we will discuss a very interesting problem in quantum mechanics. Came in this net December, this net December exam. Okay, so what is the problem? The problem is that a particle of energy E, they are mentioned that it is plus E, not minus E. So that is very interesting actually. Is scattered of a 1D potential of lambda into delta x. The lambda is real and positive, and the transmission amplitude for this is t plus, and if the potential is minus lambda delta x, then the transmission amplitude is t minus. So the question is, in the limit epsilon e tends to 0, capital E tends to 0, what is the phase difference between t plus and t minus? Okay, so now thing I want to mention, many of you guys can do this mistake that when we talk about delta potential, we normally talk about the bound state solution, and the negative delta potential. We usually work with minus lambda delta x and do the bound state solution. But in this problem, we have to deal with the scattering state solution. So actually, in exam time, it's a little difficult to solve this problem. So okay, then now look at the solution. So this is the Schrödinger equation except at x is equal to 0. That is the standard Schrödinger equation. And note that here the E is positive. Now we are looking scattering set. So E is positive. I am highlighting this word many and many times that E is positive because it is very important to keep this thing in mind. Now, yeah, so d2 phi dx2 is minus k square phi now. In the previous case, when you do bound state solution, this will be plus k square. Now it is minus k square, where k square is 2m e by h cut square. So this kind of Schrödinger equation, this kind of differential equation have the two solutions superposed, e to the power ikx and e to the power minus ikx, where a and b are some amplitudes. Now look, some things I mentioned already, that this is phi suffix l. L means the left hand side solution. This is the superposed with e to the power ikx and e to the power minus ikx for x less than 0. And for x greater than 0, I write as psi r, which is also psi tt for transmitted and r for right. The right hand side solution is only the transmitted solution, that is c e to the power ikx, where c is the transmission amplitude and here a and b are the incident amplitude and the reflected amplitude. This is the incident part and this is the reflected part. I draw the diagram pictorially that this is positive of lambda delta x, and this is the incident part a to the power I kx, and this is the reflected part b to the power minus kx, and this is the transmitted part c to the power I kx. This thing is same like the potential step potential problem, where you have a step potential of v naught, and when you try to solve the transmission amplitude and reflection amplitude, you will solve this in same technique, that something is incident, something is reflected, and some of the part is transmitted. So I am doing the same thing here. So this is the left hand side solution, this combination of incident and reflected, and the right hand side solution psi r is only the transmitted. So now same techniques, that wave function is continuous at x is equal to 0. So a plus b is equal to c. This is one relation. And the second thing is, we have to use the same technique, rise the Schrödinger equation. I am doing this with plus lambda delta x, the positive kind of delta potential. And when we get the final result, we can replace this by minus lambdas. So we will integrate this Schrödinger equation in the neighborhood, a very small neighborhood, epsilon neighborhood of 0, x is equal to 0. So this term will lead us to this d phi r dx minus d phi l dx. We saw it in the previous problem also. This delta function potential integration we already know, and in the phi x term I am using this phi t, or the phi r, the right hand side part. You can also use the phi l here, doesn't matter, it will not affect because c is equal to a plus b already, and the right hand side is 0. So you can now differentiate this phi r and phi l and put x is equal to 0. So after a little bit of algebra, simple algebra, you can get some relations with A and C, where A is the incident amplitude and C is the transmitted amplitude. I want to mention another thing, where it is C, it is actually T plus. In question it is mentioned at T plus, but I am writing it as C. And in the final result, I will make this C as T plus, because C is the transmitted amplitude. I already mentioned here. C is the transmission amplitude. So according to question, this C is T plus actually, but I am writing it as C. Okay, so this is some relation with A and C, and we get the relations, and there is a iota term here. So it is clear that it is a complex number. Now, so now this is the C by A term, which is 1 by 1 plus Im lambda by h cut square k. This is like a complex number, and you can find the argument and the amplitude of the complex number, that uh, if you have 1 by A plus Ib, then multiply upper side and lower side by A minus Ib. I am doing the same thing, and you can write it as the e to the power r e to the power I theta, where cos theta is this term and sin theta is this term. So tan theta is m lambda by h cut square. This is simply a class 11 complex number problem. I am just doing this complex number problem for here. And now once I get this tan theta, now we can simply use for v is equal to minus lambda delta x. This lambda should be replaced by minus lambda everywhere. So for minus lambda delta x, c by a will be e to the power I theta 1 plus m lambda by h cut square k. This theta will be in the previous time it is theta. Now it will be replaced by minus theta, so it will be e to the power I theta term, because lambda will be negative. Lambda is negative this time. So this is for minus lambda delta x. So according to the our given question, which are we have writing as C, is T plus is A by this amplitude part into e to the power minus I theta, and T minus is this amplitude part, this is the modulus part, and this is I e to the power I theta. So the phase factor is here is minus theta, and here is theta. What you can say that you can say that this is theta and this is minus theta according to your convention. So now when capital E tends to 0, that means the energy tends to 0. That also means that K tends to 0, because K square is 2 me by h cut square. So when K tends to 0, now look at the expression for tan theta. Tan theta is m lambda by h cut square k. So if K tends to 0, then tan theta surely tends to infinity. And tan theta tends to infinity means theta is equal to pi by 2. So the phase difference between T plus and T minus, that is equal to, here the phase part is e to the power minus I theta, and here it is e to the power I theta. So the phase difference is 2 theta. So 2 theta is pi. So as theta is pi by 2, so 2 theta is pi. So the correct answer will be option B. So if you go technically, it solves the Schrödinger equation and you can finally get the result. But in exam time, it will be a little difficult. I agree, because there are complex numbers and these are unusual a little bit. Most of the people don't have enough patience to do this in exam. Okay, so this is actually a good problem in quantum mechanics. And okay, so thank you. You can you can suggest and comment in the comment section if you have any doubt or anything like that. Thank you.